Hi everybody, this is Cal with a reading guide on sections 1.1 and 1.2. Uh, as this is the first reading guide, let me say a couple of things about how these will work. Basically, what I aim to do here is to give you guys just a sort of bird's eye view of the reading that you need to do and some things to look for in it. I will not necessarily interface directly with the material, although I will say a thing or two about it, and maybe how you want to look at it. It is also possible that I will occasionally answer questions that are on your reading quiz, so it might help you to take a listen here. Now, for sections 1.1 and 1.2, I will have presented 1.1 before you maybe are watching this reading guide, so we may have covered some of this stuff in class already, but we'll see what we can do here. So, let's start with section 1.1, Sets and Functions. And the beginning of this section kind of gives you the basic idea of what is a set, what is an element of a set or a member of a set, and some notation to use for things like X being a member of A being a subset of B, and so on. You do want to know the difference between a subset and a proper subset. And definition 1.1.1, two sets being equal, is surprisingly important, especially the blurb right below it about how to prove that two sets are equal. You really need to know that. That comes up again and again and again. You want to keep reading pretty carefully below definition 1.1.1, including the paragraph below it, and you definitely want to know the notations for the special sets halfway down the page. These, again, are notations that will come up again and again and again. The font there is called Blackboard Bold. You'll see me use it in class all the time. Example 1.1.2 is just a couple examples of sets. They're maybe not so terribly interesting, but they can help you get used to some various notations. We talk about set operations starting at the bottom of page 2. And these, again, are pretty fundamental. You definitely want to know all these operations, and the pictures below definition 1.1.3 are also very important to have in mind. What I'll say in general about this book is it does a good job of making precise definitions that you can use, but it doesn't necessarily do the world's best job of conveying intuition. Now, in definition 1.1.3 with these pictures, it does do a pretty good job, but there will be cases even later in this section where intuition is maybe left by the wayside, and we'll get into that. Theorem 1.1.4 it's nice. I'm not going to say that it's going to come up a heck of a lot, but it's nice, and more importantly, its proof is really important to read and understand. It's a really good example of a proof where you're showing that two different sets are equal. So do pay attention to the structure of that proof and how it works. At the bottom of page 3, we talk about infinite intersections and unions of sets. You do want to make sure that you understand how those work. That goes on to the top of page 4. Starting a little bit down into page 4, we talk about a definition of functions. Now, this next page and a half, talking about Cartesian products and the definition of functions or mappings, is a pretty good, precise definition of a function. I will say, however, that definition 1.1.6 is not the one that I'm going to use. I'm really going to use this little blurb that they have at the top of the page. I'm going to consider a function to be a rule of correspondence that assigns to each element x in a domain A, a uniquely determined element f of x in a codomain B, and words like domain and codomain I will have talked about in class, so you'll want to check out your class notes for this little bit. The definition of functions here is one of the places where I wildly disagree with the way the book handles it. I think that it's all about the intuition. And the picture that the book provides on page 6, about halfway down the page, of a function as a machine is really a good way to visualize a function. The picture at the top is really good too. You have a set A, a function does something to it, and it spits out results in a set B. At any rate, this whole bit from pages 4 to 6 is a really good thing to read and make sure you understand at least the pictures and what's going on here. At the bottom of page 6, we start talking about direct and inverse images. These, again, are vitally important definitions. Make sure you know them and understand the pictures behind them. So this picture halfway through page 7 is a really important one. The remark at the top of page 7 is also really important. When I use the notation F inverse of H, I do not mean an inverse function. I mean an inverse image of a set, and make sure you know what that means. The examples, 1.1.8, are really, really important. I might recommend that you draw out the pictures that go with those examples. Try and understand why they work the way they do. Starting at the bottom of page 7, we talk about special types of functions: injective, surjective, and bijective functions. These are vitally important, especially the idea of bijections, which is going to be really, really important in 2 sections when we do section 1.3. Do make sure that you read this whole bit pretty carefully. Example 1.1.10, it's a reasonable example, but a little bit messy. I would recommend that you work through it, but yeah. Finally, at the bottom of page 8, we talk about inverse functions and what you need in order to have an inverse function, which specifically is a bijection. I would recommend that you read carefully through that definition and the accompanying example and remark. Then on page 9 we talk about the composition of functions, which again is a really important definition. There's a really good picture here of it. And I would read the example as well. Pay attention to what's going on with domains and ranges in this example. Okay? And then there's a theorem, 1.1.14, which is very important, and proving that theorem is part of your homework. We do talk about restrictions of functions on page 10. This is pretty important, especially when you're talking about, restricting a function so that you can take an inverse. And we do this all the time with things like, the square root being the inverse of the square function. Well, it's not the inverse of the entire square function, it's the inverse of the square function on the positive numbers. We also get things like inverse trig functions this way by restricting the original function so that it's 1-to-1. So that wraps up section 1.1. Let's move on to section 1.2, which is a little bit shorter, but no less important. Section 1.1 lays out a lot of the fundamentals that we'll be using throughout the entire class. Section 1.2 lays out a really fundamental proof technique called mathematical induction. So do read this section pretty carefully on the whole. 1.2.1 gives you an axiom, or in other words, a basic tool that we are kind of just assuming about the natural numbers that we're going to use to prove the things in this section. Make sure that you read and understand the principle of mathematical induction and read its proof. Make sure you understand how that works. The reason that it's important, though, is kind of covered at the bottom of the page. This is vital. We use the principle of mathematical induction to prove things, and specifically we use it to prove statements that have meaningful value for each natural number. So this is a statement that I have to evaluate for the number 1 and for the number 2 and for the number 3 and every single natural number going forward. The principle of mathematical induction gives us a tool that we can use to prove such a statement without having to check every single natural number, which there's infinitely many of them, so that would be really hard to do. So make sure you read the principle of mathematical induction as it applies to statements. We have terminology at the top of 13, things like the induction hypothesis and so on. And 1.2.3 kind of gives you a second version of the principle of mathematical induction. The difference between this and 1.2.2 is that this version lets you start with any number instead of necessarily just 1. So maybe I have a statement that isn't true for 1, 2, 3, and 4, but starts being true with n equals 5. 1.2.3 gives me a tool to handle that case. Read 1.2.4 carefully. It has a lot of different examples. It goes on for a couple of pages. I recommend that you understand as many of these examples as you can. We will cover some of them in class, or similar things in class. And finally, 1.2.5 is easy to gloss over, but it's one of these things that it's really useful to know about when you need it. It's the principle of strong induction. It has the same flavor as the principle of mathematical induction, but it gives you a little bit more power on the inductive step. And we'll talk about it a little bit in class if you don't understand what it's saying, but make sure you've read it. And that covers sections 1.1 and 1.2. Thanks for watching.